The day before April Fool's Day 2004, I published a booklet called The Vinland Map, A Short Summary by the Vinland Map Study Group. According to the cover, it was a reprint of a copy which had fallen through a metadimensional wormhole from another universe, where the team which had been hired to study the map for Paul Mellon in the early 1960s spotted that it was a hoax, and all subsequent studies were mere academic exercises. A few unlucky folks got free copies, including Yale University Library and Granite Productions of Aberdeen, Scotland, who were making a documentary about the map to be shown in British and American versions later that year. Not quite enough later, as it turned out, and I saw the British version, sadly lacking my input, on 15th May. However, the producers were genuinely interested in some of my ideas, and it wasn't too late to revise the website for the American version, The Viking Deception, which was nice. Also interested when he heard about the book was Dr. Kenneth Toe, who had been studying the map since being introduced to it in the 1970s by his former Smithsonian Institution colleague, Jacqueline Owen. After reading it, he emailed me and kindly supplied a long list of corrections, which, after due discussion, led to the creation of a free online PDF version of the booklet, completely revised and stripped of its April Fool Other Universe nonsense. The motivation for the TV documentary was the publication of the definitive history of the Vinland Map, including a detailed theory about the person who created it and his reasons for doing so. The author, Kirsten Siver, a Norwegian-American specialist in the Norse exploration and colonisation of the North Atlantic, to whom hoaxes like the Vinland Map have been a frequent source of annoyance over decades. I was one of the first purchasers of her book in July 2004, and I learned a huge amount from it. The big catch was that I didn't believe for a minute in her identification of the hoaxer and his motives, because, as I had written in my own book, the map was unique in too many different ways. In May, Kirsten had attended a conference in Copenhagen to speak about the medieval ivory trade, in which walrus tusks from the North Atlantic colonies had been very important. The organisers also persuaded her to speak at a special evening session on the Vinland Map. At this session, unexpectedly, Jørgen Simonsen, a Danish businessman with an interest in the Viking era, brought in Jacqueline Owen to give a talk. A consequence of this evening was a conservation study of the Vinland Map and its companion documents by experts from the Royal Danish Academy of Fine Arts and the Royal Library, arranged by Simonsen. This study, published in 2005, confirmed that the two halves of the map were separate, only held together by the binding strip on which they were glued, and it produced one piece of information I would later find useful. The average thickness of the Vinland Map parchment is just 0.11 millimetres. Later, to be precise, was 2008, when Kenneth Toe and Kirsten Siver were joined by Professor Robin Clark, co-author of the most recent analysis of the Vinland Map Inc., to write a rebuttal to a thoroughly misconceived paper on the map by carbon dating specialist Garman Harbottle. I was asked to comment on their work as it progressed, and, in the course of discussions, I noticed something very odd about the controversial 1985 analysis by Professor Thomas Cahill's team at the University of California, Davis, which had famously found the quantity of titanium in the map ink to be several orders of magnitude smaller than the previous analysis by Macrone Associates of Chicago in 1973. By 2008, there had been many quantitative studies of ink composition, mostly using the same technique as Cahill's team, particle-induced X-ray emission, or PIXI for short. The Vinland Map's two companion documents were universally agreed to be genuine medieval work, using a perfectly ordinary, good-quality iron-based ink. Yet strangely, the quantity of iron it contained, according to the Cahill analysis, was several orders of magnitude smaller than any comparable medieval ink. That information was published in the rebuttal paper, but I found more. In the 1987 published report, the Cahill team had stated that their 1985 setup gave a minimum detectable limit of a few parts per million by mass of the sample. In 2002, news reports about the carbon dating of the map had included photos of the triangular sample next to a ruler, showing that its area was about 2.5 square centimetres, while its weight was given as 28.8 milligrams, making about 11.5 milligrams per square centimetre. The parchment thickness of just 0.11 millimeters meant that the powerful 4.5 megaelectron-volt particle beam would easily pass right through, so the sample mass would be the whole mass, which can be expressed as 11.5 million nanograms per square centimetre. The smallest quantity of any element detected with acceptable precision in the Cahill team's analysis was 0.1 nanograms of copper. 0.1 nanograms in a sample weight of 11.5 million nanograms is equivalent to 0.0087 parts per million. By any reasonable definition, that is getting on for 1,000 times smaller than the minimum detectable limit of a few parts per million by mass of the sample. The Cahill team's analyses for all elements were too low by a factor of around 1,000. Most academic studies of the Vinland Map since 2005 have been worse than useless. The Danish conservation team, which had studied the map in 2005, went on to produce a report about its authenticity in 2009, seemingly unaware that most of their arguments had been raised and dismissed by others decades earlier. Jacqueline Ollin continued to produce papers based on the notion that the map's ink was iron-based, contrary to the substantive findings of all analyses. At the end of 2014, Professor Cahill and I began a discussion of the problems with his team's 1985 Pixie analysis, in the course of which I was led to an online copy of their original report to Yale. Unfortunately, when I read it, I became very angry with him, and he consequently became very angry with me, so what I'm left with is a collection of problems. First, something Dr. Toe and I spotted in 2008. The analyses were calibrated against National Bureau of Standards reference material 1533, but no such material exists, or ever existed, according to Dr. Toe's direct contact with the Bureau, now known as the National Institute of Standards and Technology. There is, however, a reference material 1833, which contains the same elements. Second, the Yale report contained no record of the calibration runs performed for the tests on 31st January 1985. Instead, tucked away in an appendix, there were printouts from calibration runs on 6th February, the day the raw X-ray figures from the January analyses were converted and tabulated as quantities of each element. Third, the quantities of elements measured in the 6th February calibration run against the standard reference material were all significantly lower than the quantities contained in the proper standard reference material 1833, with the difference most pronounced for elements heavier than calcium, such as titanium and iron. Fourth, the quantities of elements in the live runs on the map and its associated documents were measured relative to the amount of the gas argon, which is always present at quite constant levels in the air but is rarely found in other materials because it is non-reactive. Also, very conveniently, it's the only common element in air which has atoms heavy enough to be detected by Pixie. Hence, in the 6th February calibration, almost all the 7,387 nanograms per square centimetre of argon detected would be in the air through which the particle beam passed on its way to the target sample. 7,000 would be a reasonable approximation. In the tables of quantities, argon would always be given as 100%, meaning that another element in the same analysis which was detected in twice the quantity per square centimetre as argon would be entered as 200%. Even if some analyses went slightly wrong, the quantities relative to argon would still be roughly correct. So, if an argon figure of 100 represents about 7,000 nanograms per square centimetre of argon detected in the air adjacent to the sample, then our figure of 200 for another element represents 14,000 nanograms per square centimetre detected in the sample itself. In a spreadsheet, we could express this conversion as n times 70, or n times 7e1. In the 1985 Yale report, the conversion factor they used is stated explicitly in words: divide by 7 to get nanograms per square centimetre, which would be a slightly different spreadsheet formula with hugely different results. The difference between multiplying by 70 and dividing by 7 is, of course, 490 times. For titanium, assuming that standard 1533 really is standard 1833, the combined effect of the third and fourth problems means that the published Pixie figures which so outraged Walter McCrone and Kenneth Toe are 1200 times too small. But there's at least one more relevant problem. Fifth, the cross-section size of the Pixie particle beam was usually set at 0.5 mm wide, which was only slightly narrower than the average ink line. The analysis depended on comparisons between analyses of inked parchment and analyses of bare parchment. But if the inked parchment analyses also included an undetermined percentage of bare parchment, the comparisons would be misleading, giving falsely low quantities for elements only present in the ink, such as titanium on the Vinland Map and iron on the two companion documents. There are numerous other problems with the 1987 and 1996 published reports of the Cahill team's 1985 analyses, mostly relating to omission of data which, like the notorious loose particles in the map fold, seem to make no sense. They did indeed make no sense if the Vinland Map was a genuine medieval document, but in the next and final part of this series I will show how they make perfect sense in a forgery.